Good morning, and thank you very much for joining us. We're really grateful for your time today. Tomorrow, all are part of both days. At the heart of this event is the 110 plus hours of technical sessions. Please make the most use out of those. But also the technology lab. We've got our technology lab here once again this year with our technical sponsors supporting. And there'll be opportunities. I'll talk a little bit more about it during some housekeeping at the end of the day, or at the end of this keynote. There'll be opportunities at lunch today, lunch tomorrow, and then also we've got an evening reception tonight. So please take advantage of that opportunity at the Tech Lab. This is our 7th year of doing these Tech Days here in Southeast Michigan, and once again, we wouldn't be able to do any of those 7 without the support of our sponsors, and you can see them here on the screen behind me. So thank you to the 25 plus sponsors that are supporting us. Some have been with us since year 1 of our Tech Days. They will be featured in the Tech Lab as well as other demos, and please take the time to spend some time with them. Thank you to each of the sponsors. Each year, we aim to bring some keynote speakers to talk about topical trends. This year is the same. We're really honored to be joined by 2 luminaries, by Henry Ford Technical Fellow Jim Buczkowski, and then also by NXP's Senior VP of Engineering for Microcontrollers and Microprocessors, Kevork Kechichian. So thank you, gentlemen, for joining us. And with no further ado, I'll welcome, and please join me in welcoming to the stage NXP's Kevork Kechichian. Kevork? Thank you.
Good morning, everyone. It's a bit early for me. I'm still in San Diego time. So this is my really first big event, part of NXP. I really enjoy giving these talks. Feeling the energy in the room. Just quickly, my background, I've been in this industry, and by this industry I mean semiconductors for probably 30 days, show 3 decades. So I was very young when I did that. So, so what I'm going to do is, again, my background is always in semiconductors. I started doing research in low power circuits, Reed-Muller constructs for some of you who've done that or know what it is. Then eventually moved to the consumer side, doing graphics chips for ATI. Back then it was pre-AMD days, and then media processors for LSI, few startups, and then my latest stint was with Qualcomm. I was 12 years there, managing all the Snapdragon chip development globally. And then lately we've been doing some auto-related and machine learning-related chips. So really, high volume production, multi-billion, actually close to 10, 12 billion transistor chips. So that's the excitement for me, is really bringing my background in these large systems, large projects, and into what NXP is all about in the auto industry. So the talk is really going to be about my perspective coming in and what I think the challenges are. And of course, there's lots of platforms already available today that was predated my tenure here. And I've been here, by the way, at NXP since April, so I'm relatively the new kid in town. So, and then I'll talk about some of the challenges, and then we'll see how this whole industry is going to evolve and benefit from really the trends in the semiconductor industry. So this is nothing new. Really, all these intelligent devices, systems have the same kind of paradigm built into them. There's really there's the sensors, which kind of maps the surroundings, what the mapping of what the different obstacles are, or how they can navigate through different systems. And then there's a processing part, the thinking part, and eventually connectivity and all the other stuff that's actuators and acting. And you see at the bottom there, different devices of varied complexity, usually increasing from the right side to going to the left. And really today I'm going to talk about the thinking part, the need for high performance, actually high performance everything, whether it's computing power or bandwidth or or connectivity, and I'll talk about all of that. But we have to remember that the underlying concept and what makes NXP special, not just in the industry that we're in, but also globally, it's really the knowledge about safety and security and how that is important, especially in systems that are very mission critical. So a bit about Moore's Law, since I've been doing this for almost 2/3 of it. The phase one is really about semiconductor manufacturing, how we can cram more transistors, more functionality into given real estate, silicon real estate. And you see there listed really the steps that happen. I mean, first of all, really how we can make the transistors smaller. And that was really through lithography. The masks were getting smaller and smaller to the point where it was becoming very unmanageable, both for EDA companies, but also from a manufacturing perspective to get the robustness of these large chips, and then get it to commercially viable solutions, right, from a yield perspective. Of course, with shrinking transistor, there's also the side benefit of getting higher performance. Power would get lower. And then the next phase was really looking into how we can make the connectivity, the connections, much faster, much more robust. If you look at any large SoC, complex SoC today, everything is dominated by the wiring within that system. And it becomes a challenge from managing congestion, managing the power profiles, and simply, I mean, imagine if you have the 3200 megahertz DDR interfaces, you need all that signaling at that speed to be managed within a chip. And then eventually, maybe it was a decade ago, 12 years ago, people started looking at three-dimensional constructs, and then there were two different paradigms there. One of them was really taking the planar CMOS and moving it into the third dimension, just from controlling the dimensions of it, but also the power profile and how the minimum VDD that can operate there. And also now we're moving into what's called nanowires and nanosheets. So most of you have seen this graph. The top one is really the transistor count, and that's fairly linear. The trend has been, I mean, I know it's Moore's Law, but it's really a self-fulfilling prophecy where the whole industry is geared towards making that happen. And every few years we say, this is it, the end is here. And then we keep on getting surprised that things are still going to increase, and then densities are going to increase. Now, the interesting part is if you look up to, let's say, 2005, every other metric has been growing in a similar way, right, with the transistor. There's some linearity there, and things were increasing. And then I'll talk about the other part of it, post-2005, in a few slides. A quick primer here. So for those of you who are not familiar with the terms and the constructs, the one on the left is really the transistor, the unit of the transistor. It's a very simplified version of it. So you see the sides that are kind of shaded blue. Those are what we call the source and a drain. And the green on top is the gate that controls the flow of current from one side to the other. And really, it's a switch, on and off switch. So if you look at the planar construct, and that's been in the works for, like I said, almost 50 years in different incarnations of it, to control, let's say, the power of it, to have the characteristics of it, what you can play with is really the two dimensions of the gate, right? You can have the channel where things are flowing. You can have it wider. You can have the width, the other dimension wider to have more power, more performance. But really, you see the cost associated with it. As you're increasing these footprints, the dimension, the two-dimensional size of the circuit increases. So what happens is that at some point, the chips have become so big that there was no commercial or profitable way of yielding those chips. So people started looking for other constructs, plus the operating voltages were coming down significantly. So they take the channel side and then they pull it up, and that really becomes the FinFET. And in this diagram, it really shows like a rectangular shape in the cross section, but really it's a fin. So it has a pointy top there. And now you see, instead of controlling the current flow through one dimension from the top, now you're controlling it through 3 dimensions, right? The both sides and the top. And that gives you better control for really the circuit characteristics. Now, if you want more power or more higher drive, what you need to do is you need to add more fins. So it becomes a very discrete step compared to the planar one where you can almost modulate it at any dimension you want. Again, there's a problem there from really the dimensionality point of view. You need more performing circuits, therefore the size of the whole thing would increase. Fast forward to probably 3 years ago or 4 years ago, people started looking at new constructs where really it becomes 3-dimensional. So the concept of nanowires and nanosheets, where you keep on adding, you keep on stacking up these channels, if you would like, one in a wire form, the other one in nanosheet form. And if you need more performance, you just stack them up in the 3rd dimension, which gives you really the scalability. Now, this is relatively new. There's no commercially or production-worthy aspect of it yet, but the industry, the semiconductor industry, is moving there. Okay, the other aspect is going to be really the software part of it. So if you look at the concepts today, the paradigms today, or the content today, really the software content is really high. And on the hardware side, we joke always that software is easy to do. You recompile and it works, right? And I mean, look at this. It's not that just the number of lines of code. It's also the number of diverse platforms that these codes run on. Whether it's a hardware platform, whether it's actually the system that they run on, the different compilers, different OSs that these things run on. And then you see immediately that as you keep on adding these dimensionalities and the complexity increases almost as a double exponential. So it becomes very, very complex to manage this whole thing. And then, I mean, you see at the bottom, there's different areas where these systems are controlled by software, and it becomes very important to manage that aspect of the development. I mentioned complex chips. I mentioned billions and billions of transistors. Really, today, what's driving the whole economics of it is make sure we manage the software properly, make sure that's under control. And not just the expense of developing the software, but there's also quality issues, right? That has to be tested, especially in this industry. The auto grade has to be there. It has to be qualified for safety. And then now you see how expensive that development becomes, right? And then at the bottom, like I said, there's different areas where these softwares are controlling the system, the overall system. Now I keep on talking about system platforms. You're going to hear that quite a bit today, this morning, and it's very important to have that concept in mind. And then for me, actually, that was the exciting part for joining NXP, because the system for me for the last decade was really a large chipsets with the power manager, the RF front end, with all that complexity. But now we're moving into something that's very distributed system, probably close to 300 components in a car, and it becomes way more interesting. Again, the dimensionality of the complexity is just tremendous. Software complexity. So the graph there shows really the amount of memory that's available versus the lines of code. So you can look at this from multiple perspectives, but really one of them is how we're going to manage that trend that's accelerating at a way different rate than really what's available on chip or within the system. And there's different ways of managing that, and I'm going to talk about that a bit. But you look on the left side, what are the drivers of this complexity? I mentioned the variance of different platforms available, but also there are different domains. I'm going to talk briefly about domains in a few slides. We're talking about energy efficiency, most optimized way to get from point A to B, how these different systems within a car are interacting with each other. Then, of course, you put in the whole ADAS aspect of it, and that's a whole different dimension that's piling up on this. And then eventually, the new paradigms, connectivity, the user experience, and of course, that whole industry on the consumer side and all the different layers of it show up as part of this. AI, very pervasive. I mean, we lived through these industry terms. First it was the cloud, then it was IoT. But I think this one is here to stay. It's not just a fad. And AI has been around probably a good part of the last century, since the 40s and 50s. The term was coined I think in 1952, a part of a conference. But really, it was very academic because most of it needed like compute power and heavy compute power. Just to give you an example, one of the most difficult problems today in AI is really dead reckoning. And if you look at an ant colony, if you look how ants go look for food, they do zigzags and relatively random behavior for their trajectory looking for food. And as soon as they find it, they go directly back to their to the nest, or whatever we call that. That's really a hard problem. And then if you look at the number of neurons in an ant's brain, it's really 300,000 at that level. And today, people with all the neural network modeling, we're trying to figure out how we can fit those algorithms into 300,000 neurons. And it's not just the neurons that are making it complicated, it's the amount of connections. So the solutions that exist today, it's really in the billions of neurons. That's what they require, and hence the processing power. But you see, these problems are very real, and they've been with us for a while. And now that we can put these billions and billions of transistors on a chip, the compute power is really, really tremendous. So around the periphery of the car, we have the traditional aspects, just the sensing capabilities, vision, improvements in vision. And this has been around for probably the longest, computational vision, high-resolution cameras. So not only these are important from mapping the surrounding of a car, but also internally see what's happening within the car, within the cabin. Then you have all the traditional car-specific functions from powertrain, and then from all the controls within the car. And of course, the security aspect is going to be very important because think about this: the AI or these chips or these systems are very good at taking large data sets and then inferring some conclusion from them, right, with very high probability of success. So from a security perspective and safety perspective, they can look at all the data that's happening, and based on their previous training. And by the way, the training is done in the cloud, and then these systems have inference engine in them. You can think about it like an optimized shrank kind of neural net processor that they can monitor and digest the data. So from that perspective, we see a tremendous number of applications in that area, and it's completely different than the traditional, if then else, very conditional, very sequential software development. So there's lots of excitement in here, but also it's adding on the complexity side. Definitely, this is, I would say this is the nth dimension, depending on which paradigms you're looking at. Safety is very important, security is very important, and really you can't separate the two. When you have one, you have to have the other one. There are different aspects here, and I'm going to just zoom in on the second one from the left there. It's really about device reliability, and it goes back to all the manufacturing techniques, all the robustness. It starts all the way probably 5 to 6 years before a chip or a system finds its way into the end product. So you're talking about the technology definition, all the way from the transistor layers, the margins, and then how you're going to make sure that all these transistors do not fail just from a manufacturing perspective. And that's very important because key is not only you have to guarantee the non-failure with low defect rates, but also you have to make sure from a system perspective that if and when a failure happens, there's this concept of graceful degradation, and that would take the vehicle in motion into a safer environment, safer speed. So all of these systems are built on top of each other. And of course, you look at the safety from a security perspective. You don't want these systems to be hacked because everything is connected these days. You don't want someone else taking control that is not part of the root of trust, and then controlling the vehicle, and then eventually using for purposes that aren't intended for it, right? And I mean, a car is something where you have your family driving, your kids, your friends, plus it's going to become an environment that's really familiar to you, right? And I will talk about that briefly. The other three dimensions of complexity, the number of data generated by the sensors, by the driver, within the car, and it's really exploding. And part of the issue is what to make with that data. You know, some of it is very non-interesting. I mean, you're driving on a constant speed on a freeway, and it's the same data over and over, but suddenly interesting things happen. So part of the learning is going to be how to kind of zoom into these interesting things and interesting windows, and then how to extract the information that's going to be helping improve the system from all this terabytes and petabytes of data. The network bandwidth is very important. Now I'm going to talk briefly about the bandwidth within the car, but also all this data has to be uploaded somewhere, either in compressed form and raw form, so it can be processed. So that becomes very important. And then you see, I mean, the growth rates are clearly, I mean, tremendous. Everything is hitting, again, I keep on talking about double exponential. And then the compute performance. This is across all different kinds of compute engines, whether it's traditional CPUs that are in large numbers in clusters and subsystems, whether it's DSP subsystems, whether it's AI and machine learning hardwired kind of algorithmic units, graphics processors that can be part of this. The reason I mention all this diversity is because all of them have their optimized space from solving a problem, right? And then that's where the software becomes the challenge, where do you take, given a problem, how do you divide it up between different ISAs and different processing engines? Okay, back to 2005 and onwards. You see the curves start kind of diminishing. As the number of transistors is increasing, some of the curves are flattening out. For instance, single thread performance. Because what happens is, even though let's say pick a CPU, the Fmax is going up to we did 1 gigahertz, now 2, 3. It's very easily we can find many platforms with 3 gigahertz plus CPUs there. The problem is they're part of a system, and they're not running in isolation. It depends on the size of the code running, whether it's on chip or you have to bring it in and out. Depends on how fast you can talk to the other subsystems. So all of it is diminishing the kind of the performance, the linearity correlated with just purely the transistor side. That's one aspect. Then you have the power and thermal issues that are making things more difficult. You got to figure out in a CPU cluster where the load is going to be. So the load balancing and power management aspect of it become very critical, and could be part hardware, part software. So how to solve all of this, right? And of course, the first thing that the industry hit was really number of cores. If you double the number of cores, you won't get twice the performance, right? You're lucky if you hit 1.2 or 1.3 or 1.4, right? And really optimize for certain applications. Now, what do? We have 64 cores. You have different cores, different ISAs. So this is where the focus is shifting really. In addition to the manufacturing advancements, you're shifting the focus into more the architecture side, more the system side. So we're looking at, for next generation products, and actually some of them are already implemented, how we partition this architecture so we can harvest, from a system perspective, this linearity from a transistor count. So we're looking at multi-die modules with very short range, high-speed interfaces. We're talking about chiplets where they have like slices of performance, performance engines on them, so you can connect them in different configurations. We're looking at mostly my involvement has been really heterogeneous architectures where you have different ISAs on a system, right? The concept of memory coherency has been around since the 80s for a CPU cluster, but now you take that, you bring the GPU into it, right? You have a cluster of GPUs that are running things in parallel, and you need the memory coherency to improve that performance, harvest that linearity. What do you do about the neural network processors? They have to be part of it. So you see, these are really the exciting aspects of not just relying on manufacturing and relying on on the foundries to give us the performance boost. And of course, the software layer is very important and very, very critical. How to make this happen? Given a problem, how you partition it into these different systems. And it's not an easy problem to solve, right? Okay. So this is what, if there's one thing you gotta take away from today, I think this is the slide. We start at the left, traditional way of looking things. Over the last multi-decades, the car industry has been trying to upgrade the cars, get different services, different functions being added into existing infrastructure, right? And it's very important, again, talking about infrastructure, talking about platform, to understand how these innovations happened. And like I said, me coming new into this industry, I'm absolutely amazed at how these cars have evolved, and we have all these systems given the complexity. So now the evolution, natural evolution, is look at these different functions or domains and say, okay, I'm going to have a domain controller for every function. And if you look at the distribution around the car, it's really the distribution per function. So you have the traditional aspects. Anything has to do with controlling the car, controlling the engine, but also you have the new entrance there, and you have the connectivity aspect, you have the infotainment aspect. And then really what sits in the middle is a data manager, is a network manager, right? And that's where our S32 platform hits all of these with the different offerings. And I'm going to show you how we can do that scaling. And of course, the next evolution is going to be, and this is still in concept, we're talking with our partners, how to evolve this, where you move from a functional view of a car into more of a zonal view of what happens at each corner. And then what's the concept of central processing engine or central brain, and how large that brain should be, and how much distributed functions you leave to the zones. And that's really the interesting aspect that's in discussion currently. This is a very high level abstraction of our S32 platform. So we have what we call a common chassis, and basically that, of course, facilitates the hardware development, but also the software platform becomes consistent. So what happens is, if you look at the top, there's different applications or different domains that these controllers would go in. And really, from a development point of view, you add and remove certain functions around the common chassis. So, of course, you have all the safety and security stuff that's very central and very important for these platforms. But then you can add the vision aspect of it, the vision processors. And then you can add the autonomous driving aspect of it with more neural net processing, and then deep neural nets and convolution neural nets for camera and vision. Then you have really the central part I showed you, this network processor, where it sits in the middle and manages all the data traffic. And then this eventually leads to minimizing the amount of wiring in a car, reducing the weight. All of this is going to become like a positive feedback circle where things are the kind of dependency, where things are really helping each other to improve the systems. And then back to software. Really, what we're trying to do is facilitate all these complexities and then make it manageable without having to add the same amount of complexity from a development perspective, right? And it's not just this is NXP specific. This is industry-wide. All our customers have to face this paradigm where these trends and complexities are increasing, and you can't keep on adding people for these developments. You have to find a way to scale, and that's where part of my excitement is to bring this to NXP. Okay, so here we have existing platforms, and then you see we have, of course, I talked about the S32 platform. There's the i.MX platform, which is well known, and in the media side and infotainment side. And then the one on the top is really Layerscape, all the technology that we have from network processing. So what's really happening is again, this predates my time. People looked at it and say, hey, there's lots of commonality here. Why don't we create this common chassis and then start building on top of it? And then we take, depending on the application, we can take the elements that are most important for that particular application and emphasize them or add more horsepower behind it. So for instance, the domain control that sits in the middle has lots of technology coming from our network processing and digital networking group. And there's lots of IPs that coming there, including software, including hardware. And then same thing goes for our media processing. And that's why it makes it very easy to build these platforms. Now, just to summarize here what I've been talking about, really, I talked about everything on the left side in a very, very brief way. But what we're trying to do is have a way of impacting and benefiting everything on the right side. And then you see most of it has to be with the user experience. Most of it has to do with safety and security. We want to make someone sits in a car, it's all seamless. Things are working. You bring in your devices, your car becomes really an environment that you're very familiar with. And then finally, we have an announcement today. I think this is EIQ Auto. This is really our framework, NXP's framework of how to make deep learning available on all our platforms and make it easy for software developers and system developers to be able to harvest that. Just quickly on this, there are studies that today, a high school student with a relatively decent performing laptop, with all these frameworks available, they can write a neural net, a machine that can beat a chess grandmaster. Something that happened a couple of decades ago with Deep Blue. Some of you remember that. So it's truly amazing how this whole enablement is going on. And finally, we're really a global company. People ask me, especially new guys coming in, where's the center of gravity? NXP has no center of gravity. We're very distributed. We have centers of excellence throughout the globe, and then we try to co-locate with our customers, and it's truly a great technology driver for all of us. Okay, and then with that, I'm happy to invite Jim Buczkowski, Henry Ford Technical Fellow. Please give him a warm welcome. Thank you.
Good morning, and thank you, Kevork and Jim, as well as Alan Rook, for inviting me to speak today. I feel a little bit like the nostalgia historian here. I celebrated this year 40 years with Ford Motor Company, and so when it comes to automotive electronics, I kind of grew up in the age of automotive electronics at Ford and have seen it emerge over many, many years. Today, my role is as a technical fellow in the Research and Advanced Engineering Organization. I focus very heavily on technology trends, trying to bring new innovation and technology to try to prepare the company for Ford's future. But I've had a lot of history over 40 years with Ford Motor Company and in the electronics division at Ford, which eventually became Visteon, in electronics manufacturing, in IT, in several areas, quality and product development. I ran the electrical systems organization about 10 years ago during launch of Sync and so on. So I've been very fortunate and honored to have a lot of different experiences in the company. But let me take you back a little ways, and probably very few, if any of you, recognize some of this stuff. But in fact, in the upper left corner, this really, well, actually the whole slide displays the relationship I've had with NXP and its the companies before Freescale and Motorola over the many years. So I go back a long ways with NXP. In fact, the upper left corner was the Motorola 6800, if anybody remembers that. Between my sophomore and junior year in college, spent some time at Ford Motor Company as an intern using the Motorola 6800. And it's kind of interesting because the other nostalgic piece is you're here to learn a lot about NXP products. I remember being in Motorola sessions learning about Motorola products very similar to what you're doing here today. Of course, a lot simpler back then than the kind of complexity you're working with today. But certainly I've been involved with Motorola as they took over the responsibility for a custom 16-bit microcontroller we used in our EEC4 powertrain control system. Advancing to P-Tech, that P-Tech was the PowerPC, if you recall, or probably some of you, it's before you were born. But IBM, Apple, and Motorola worked together on a 32-bit RISC architecture called the PowerPC for Apple's computers. And Motorola took the product for embedded, and we were developing it for our advanced powertrain controller to the right as an early prototype. And then more recently, in the center on the top is our Sync Gen 1, which used the i.MX product for our first generation of Sync product. And to the right on top, your right, my right as well, or my left, I guess, here. But that's the Sync Gen 2 product, which used the i.MX. So we've got a long history of working together on automotive electronics and a really strong success story working together, and we expect it to continue in the future. Now back to today's role for me, and I want to spend a little time talking about what they've asked me to really reference is technology trends going in the future in the automotive industry. And as I mentioned, one of my roles in Ford as a technical fellow is to help determine or guide the company on what we think what tech trends are really important, are going to affect the Ford Motor Company. So this is a result of our 2019. It's actually a full book that we put together that we present and share with the company to help drive our technology strategy, where we invest, where we do research, how to drive more technology and innovation in the company, and how these areas will affect our product in the future. And across the top, computing, software and simulation, artificial intelligence and connectivity, cybersecurity and trust, advanced materials and manufacturing, and across the bottom, sensing, clean and sustainability, robotics and biotech. Today, I just want to focus on a couple of these. My voice is changing. I just want to focus a bit on computing, artificial intelligence, connectivity, cybersecurity, and sensing and visualization. Kevork really talked to some of these subjects already, so that somewhat reinforces some of the comments he made as we see it from Ford. But you notice in some of these areas, things like bio and nature, and you might ask, why as Ford Motor Company would we worry about that, or would we even want to track that? Well, there are a lot of things going on in biotechnology and nature relative to materials. You guys are familiar with what's going on with the meat and impossible meat and so on, but there's a lot of opportunities in biotech that could affect the way we do business. Things like growing leather as opposed to using it from livestock that consume a lot of CO2. So again, when we look at this, it's very broad. It covers a lot of different subjects. Putting it in 11 categories is really summarizing it, but it's really important for us to help set the direction for the company. So let me go through a few of these pretty quickly. In the trends in computing, as Kevork mentioned, there's a lot going on in terms of purpose-specific compute architectures. Driving power consumption down, driving performance up. Really, we're in a software-driven hardware environment these days, and so creating more processors or architectures that specifically help accelerate problem solutions is really critical to the business going forward. AI is obviously having a significant impact in what we can deliver now and in the future, and accelerating AI solutions is really important, as well as other areas. And in computing, we also look as far as quantum computing and what that's going to be like, and solving some of the really unsolvable problems in the future. Next, in artificial intelligence, it's been mentioned so many times, but the one thing I want to focus is artificial intelligence isn't just about autonomous vehicles. It covers a wide range of opportunities. In fact, as it says here, it's really companies that are able to use AI across the entire business, whether it's in credit, whether it's in finance, whether it's in HR, are really going to be able to accelerate their business. Also helps in terms of personalization, really understanding and delivering features and experiences that are really tuned to an individual. So the power of AI and its ability to create unique and specialized experiences is really important, not only in our products, but also in our enterprises and the way we do business. Connectivity, connectivity explosion is really fueling this. When I think about AI in the previous page, and Kevork mentioned that it's been around since the 50s, what's one of the things, not only has compute fueled it, but the ability to take data from the edge and bring it to a central place where it can be processed. What makes AI work is data. And for those of you into AI, you know about this. The data sets, you need huge data sets for learning, and connectivity has allowed us to bring lots of data to a central location so that it can be processed and enable AI and AI performance. But when we look at connectivity into the future, it's just nonstop. 5G AA is coming, it's coming even more rapidly, but even things behind it like CubeSats, if you're familiar with nanosats and so on, the potential to have satellite communication and ubiquitous connectivity, download connectivity everywhere, will probably challenge a 5G as well too. But the one thing I would conclude in this particular area is there's no one connectivity strategy that's just going to take over everything. In vehicles, we'll have Wi-Fi, we'll have Bluetooth, we'll have NFC, we'll have 5G, potentially even satellites, ATSC 3.0, broadcast, and so on. So connectivity is going to always remain diverse going forward. Cybersecurity and trust, and with connectivity, we open up a new landscape, we open up a new surface for hackers to attack, and so cybersecurity has got to be at the beginning of our design process and through the entire process end to end. Starting at the silicon all the way through the cloud, we have to think about cybersecurity and protecting personal information in our designs, and so this is going to continue to be critical. In fact, some of the tools in AI are being used by hackers these days. So imagine the challenges we have going into the future, and so everything has to be designed so it's linked together. It cannot be, cybersecurity can't be added on after the fact. Sensing and visualization, Kevork mentioned as well too. Really incredible things that are happening in our ability to sense around us. Of course, in AV, a lot of discussion on LiDAR, but even imaging radar in other forms. On the output side, when we see AR, VR, and the advancements in what AR and VR can provide in terms of experiences and processes and so on, some really incredible things, again, coupled with the processing power to process all that data. So with that as a background on technology trends, let me turn a little bit closer to the automotive. And some of this is a little bit of a repeat from a different perspective of what Kevork has shown. As you've seen more recently, in fact, from the sync history and beyond, automotive companies, specifically Ford as an example, but others as well, our counterparts, are starting to bring more responsibility for development of these systems in-house. And the reason for that is because they're becoming the character of the vehicle. They're becoming the differentiation in our vehicles. Writing the software and creating unique experiences for customers will help define the brand now and in the future. And so from left to right, you see infotainment was a key area because it also leveraged a lot of consumer electronics as well too, consumer technologies as well. Connectivity, the next phase in terms of being able to use cloud services to bring experiences in and out of the vehicle. Convenience products and gateways are really kind of the evolution path for how business and work is in design development is going to be done inside, which really leads to those bottom two layers shown there. Hardware design now is being thought of more as a build-to-print approach for these strategic areas, as opposed to relying on full-service suppliers that do everything from software to hardware. And then software platforms in-house, the reusability of software across these various systems and how we do that. So enablers within the ecosystem of silicon and software and so on are key to our future, including development tools. More specifically, looking at electrical architecture at, again, a relatively high level, you see the today's version, again, what Kevork has shown as well too, a lot of disparate systems that were installed feature by feature. So one feature, one ECU, another feature, another ECU. Starting to evolve in the direction in the middle to, including the cloud, to having some centers that do a little bit more than just a single feature, but still quite distributed and just sharing data information, really sharing signals and messages as opposed to being a true data architecture like you'd see in a data center or a cloud-based system. And then finally, the far right, really driving toward a more holistic approach of centers of compute within the machine, and the edge being really more generic pickup points for data and information. And that's kind of what you see here. From left to right, you see on the far, we now have a focus on compute centers, with the edge being centers that are picking up sensor information, maybe doing a little bit of pre-processing, also doing the actuation and feeding the center where the compute and the intelligence is making decisions. What that really allows us to do is centralize more of the compute capability so we can use AI accelerators and so on across multiple features and so on, and it also allows us to have a bit more generic command and control and sensing at the fringe at the edge inside the vehicle. So next slide here. There we go. So takeaways for you. I know we went through this pretty rapidly, but there's a strong design shift that has occurred from hardware driven in the past as an industry. We've been very strong in the past on hardware in the vehicle, and now really software is driving and defining our future. And so you see the focus on bringing more software responsibilities in-house, improving our capability in delivering software, and building the ecosystems necessary to reuse a lot of that software. Architecture is changing in the vehicle to be more like what we would see in clouds and data centers, where data is extracted and becomes available not only across systems in the vehicle, but outside the vehicle as well too. So how do we architect the vehicle, networking and so on, so that we can unlock the data that was locked into a particular, with a particular feature and so on, make it available to create new innovative experiences that draw on lots of data inside and outside of the vehicle, by the way. Data models for the vehicle. How do we actually access the vehicle from the cloud so that we can use it, we can create it in a form that opens the door to innovators, APIs and things like that give you access to the specific data. We architect the vehicle differently, and then we also architect the software differently so that people can access and build and create new innovation and new experiences by accessing that data. SoCs certainly accelerate AI and ML. You know, today's autonomous vehicle that you see running around on the road with the compute power in it is, you know, in the range of 2,000 watts. When you think about a hybrid vehicle today that can get over 40 miles per gallon, the power consumption of 2,000 watts will reduce that fuel economy in half. And so we got to do a lot in the area of compute to get it more efficient. That's why task-specific computing can help quite a bit in reducing some of the power consumption, but we've got a long ways to go yet to really get these things efficient. Connectivity, just recognize it's going to be more and diverse, right? There are going to be multiple channels, and designing systems that can use the right channel at the right time for the right cost and so on. So the expectation shouldn't be that it's going to consolidate into one system, one communication system. We'll continue to have multiple wireless access points, connectivity points. Cyber and trust is a baseline. Again, designing from the start. There's so many things when I look at my history, even recent history, not going back 40 years, but back 10 years, so many things that were built into the silicon by the silicon providers like NXP, which were intended to be used by the software guys for cyber and trust and were never used. And that can't happen going into the future. When we design silicon and we design it for software, and as I've talked to the NXP folks and so on about how important it is that the silicon design is driven to support software in the early days, and Alan and others folks remember how difficult how much complaining the software guys had about the hardware. Well, that can't happen in the future. The hardware, the SoCs, the silicon designs have to be friendly to software development. And cyber and trust is a big part of that as well too, taking what can be built into the silicon and allowing it to be built into a cyber protected design that goes all the way to the cloud. And then finally, sensing, more diverse. It's hard to predict what sensors will be like in the future, what kind of sensors we'll have. With the advancement in materials and various technologies, we have a huge opportunity. And of course, fusing sensors together is a big part of the compute platform too, is where radar may be good for one thing and cameras are good for another thing. Putting those two together really makes for a very, very powerful sensing capability. So with that, I think I'm all set for today. Hopefully that was helpful to you, and thank you for your attention, and take advantage of today and tomorrow. Have hopefully for the next 2.5 days, you have a good set of sessions and learn a lot. Thanks.
Well, thank you, Jim. That was very exciting. Partnerships are great. Maybe if you can share your vision. We've been talking about platform and software. Where do you see the software going and the complexity and how it's going to drive this whole industry? Maybe a few words there.
Well, I think, as I mentioned, software is where we're investing a lot. It is the character, becoming the character and the differentiator in the vehicle. And what is really key is that we build ecosystems of software that allow us to do a lot more reusability. These systems, when we talk about 150 million lines of code, that should be frightening, right? Validating 150 million lines of code is an impossible task. But if that 150 million lines of code is made up of a bunch of smaller, retested, fully validated modules that we can count on over and over again, that's going to make much more robust systems and allow us to build these bigger systems. It's not always the best thing to, or at least it creates more challenges for us by integrating more software into single boxes, single domains, and that makes validation a lot harder. So building ecosystems that allow a lot more reuse and validation and so on of software is really critical in the future.
Yeah, and maybe a few words about, you mentioned power, you mentioned how we have to reduce power. What's the complexity of, let's say, power management within that system, within that vehicle, both software and hardware, and how do you see that evolving?
One of the things that I always find fascinating is what power management, and you're familiar with your Qualcomm experience in the phone, right? And you've got that battery, and probably at least the high number of complaints is, talk time and everybody's fighting to put larger and larger batteries, but they got to fit them in the same space. At the same time, the silicon guys and the designers are trying to figure out ways to make the phone itself much more efficient, varying power levels and turning things on and off and so on. The vehicle absolutely has to do that going forward. So if we look at power management in the vehicle itself, we have some today, but it's not nearly as sophisticated as it's going to need to be in the future, both at the silicon level and how we can keep things alive, because today with connectivity, we actually want to keep the vehicle on all the time, not fully on, but be able to listen and communicate constantly. And so that's, the days of, we got 30 days of 12-volt battery life and then everything has to shut down is going to be a big challenge. And so power management in the vehicle is going to be critical going forward.
Thank you very much. This has been very insightful. Thank you, Jim.
Thank you.
All right, thank you. Thank you to both Jim and to Kevork. If we could just have one more round of applause for our two keynote speakers. Thank you very much. Thanks, gentlemen. Jim, thank you for the brief trip down memory lane, but also even more so the view towards the future and some of the future trends. Very, very interesting. Kevork, welcome to NXP. We're delighted to have you on board. My teammates will tell you that I'm one that's particularly fond of illustrations. They probably roll their eyes when they tell you that, but they will tell you that I'm fond of illustrations. And your illustration on AI of the ant and the ant meandering and then coming back on a straight line is a great visual. So thank you very much. Thank you, gentlemen. All right, just a reminder. This is just a couple of housekeeping items, and then we'll move on to the technical sessions. Again, Technology Lab, great opportunity to see not only our very valued sponsors who were very appreciative of, but also to mix and network opportunity at lunchtime today, again tomorrow, and then please do join us for our reception this evening. A couple of items to highlight in the Tech Lab. One is there's a demo today, a company that NXP has collaborated with called ART in Italy. And by the way, on the lower, I'm doing the same thing, Jim, that you did. Lower right, so it's got to be everybody's lower right. On the lower right of the screen, you see ART Advanced Solution. Don't Google Italy ART because you'll never find them. But if you do ART Advanced Solution, you will find them. So NXP did a collaboration with this Italian company called ART. There's a cluster in the Tech Lab, and today, in fact, concurrent with this keynote, we have a press release going out announcing that collaboration is going into production into a luxury Italian sports car. And I'm not allowed to mention the name of that sports car, otherwise we have to pay some royalty. Instead, what I'm going to do is petition that next year's giveaway will be one of these Italian sports cars. I don't know if I'm going to get that through or not, but it is in there, and that's going to be the reason also that we'll have a sheet cake in there to celebrate. So in the Tech Lab today, there'll be some cake celebrating this collaboration, but there is a demo in there as well. So have a look at that. iDatum X8 Quad Max is the underlying technology that's there. Ron Martino was going to kick me off stage if I didn't mention that. Last year and again this year, we are featuring some giveaways, and this is the quote-unquote badge. And you know, you heard Jim Buczkowski talk about trust and cybersecurity. Well, at this DEF CON event, there's a car hacking village that's a very popular activity that's there. This year, the quote-unquote badge that was the giveaway there is an autonomous car, but can also be controlled by a smartphone. I thought this was my application engineering team playing a joke on me, an autonomous car that could be controlled. That's a remote control car. I mean, but no, it can be done both. It can be autonomous, it can be controlled by a smartphone. It's loaded with NXP technology. We're giving 2 of them away, and all you have to do is drop your badge in the bowl in the Tech Lab, and you're eligible for the giveaway. The trick is that it's not obvious where that bowl is, so you've really got to get through that Tech Lab to participate, and then we'll be giving that away. By the way, it's loaded with NXP technology. If they're for any of the people in purchasing that are here, you know, if you want to buy a bunch of these for your company as holiday gifts, we're happy to accommodate that as well. Okay, so that wraps it up. Again, thank you, gentlemen, for the outstanding keynotes. We will take a brief break, and then we'll get started on the technology sessions. And thanks again for your participation here today and tomorrow.